Check. All right, my okay, can I? Hey guys.
You Googled what an Americano is.
That's a lot of water.
Is it two espresso?
Oh, 2 espresso.
Yeah. So
Oh, you guys are the best.
there you go.
Yeah.
I did.
Check.
Honestly, we spill so much coffee on this floor.
Check.
Like, I feel bad for the maintenance staff, but
Yeah, it's only have one for 2 hours.
I know.
I think so.
All right, welcome everybody. Thanks for coming out to Matt Mitchell's dissertation defense. I'm David Poland, his PhD advisor. Matt is going to tell us all about some work he's been doing on precision bootstrap studies of fermions and stress tensors in conformal field theories. The defense will have 2 components. First is a public lecture to all of you. That will be in the first hour, and everyone in the audience should feel free to ask questions throughout. And then the second half of the defense will be questioning by the dissertation committee. So all the members of the public who want to wait around for after that can hang out in the first floor lounge while Matt is being questioned in the second half. So without further ado, I think we'll get started, and Matt will tell us about the work that he's been doing.
All right. Thank you, David. Can everyone hear me? Okay, can Zoom hear me?
Yes.
Yes.
All right, everyone on Zoom, don't forget to mute your mics. Let's get started. Where's my pointer? Okay, so good morning, everyone, and welcome to my thesis defense. Today I'm going to be talking about precision bootstrap studies of fermions and stress tensors in conformal field theories. And for those of you who are not theoretical physicists, I promise I will explain what all of these words mean in due time. So first, a little bit about the structure of this talk. I'm going to start by presenting some background information about CFTs, which are the things I work on. I'm then going to explain the conformal bootstrap, and then we're going to go into some of the results from my thesis work. Yeah, so without further ado, let's get started. So I study conformal field theories, which are what you get when you ask what boiling water can tell you about elementary particles and vice versa. On its face, this seems like a bit of a crazy idea. Here is a quote from conformal field theorist Alexander Polyakov to that effect. But as we shall see in due time, it is not a crazy idea. To explain why, I need to introduce a few concepts. First up, criticality. So this here is a picture of the phase diagram of water. Now, as you all know, water experiences a phase transition between solid, liquid, and gas, but that only happens at atmospheric pressure. If we allow ourselves to vary pressure as well, we get an entire phase diagram, which has a new kind of phase transition, like a qualitatively different kind of phase transition called a critical point. A critical point is, as you can see here, is a point where the first order phase transition, like the coexistence curve, like ends. We get what's called a continuous phase transition. And past it, we have a supercritical fluid. Now, liquids at these liquid vapor critical points look really cool. So here's an example not in water, but in ethane, which has the same dynamics. On the left, we see a liquid phase. As we vary the pressure and move towards the critical point, we get this critical fluid. It's opalescent. It looks very cool if you see it in person. And then past the critical point, we have a vapor. But yeah, that is one example of a critical point. Another is in something the physicists among you might have heard of, the Ising model. So if you want to build a toy model of a magnet, this is the easiest one you can write down. We put a bunch of spins on a lattice. The lattice can be in 1D, 2D, 3D, 4D, etc. We define an energy. We say that conditions are more energetically favorable when neighboring spins are aligned. And we also add an external field term if we're like applying an external field to our magnet. Now, what this is going to do is at low temperatures, all of these spins are going to want to align. At high temperatures, when higher energy states are more accessible, we are on average going to have random spins. And there's going to be no long range order. So if at zero magnetic field, we also get a transition from a ferromagnetic phase to a paramagnetic phase. And this right here is a critical point. In fact, it's the same critical point as in the water phase diagram because it is described by the same CFT. This is called critical universality. And it means that studying critical points is like studying critical points as abstract objects can tell us about a broad variety of different phase transitions. So let's look at a critical point and see what we get. So critical points, as opposed to the first order phase transitions you all know and love, are characterized by scale invariance. So that means as you zoom in or zoom out, the dynamics of your system do not qualitatively change. Here is a magnet at low temperature. It has long range order. On average, all of the spins look the same. At high temperature, it's disordered. If you zoom out, this is going to basically look like a mix. But at the critical point, what you do is you have a bunch of domains, and if we zoomed in on like this little patch here, it would look qualitatively the same. There's sort of a fractal like self-similarity there. And this is true at critical points because everything we can measure about critical points falls off as a power law. So the heat capacity of a system near its critical point, T parameterizes how far we are away from the point in temperature. The heat capacity varies as a power law. The average magnetization varies as a power law. The magnetic susceptibility varies as a power law. And the correlation between two spins as a function of their separation, believe it or not, that is also a power law. But what are these exponents here? I've written them as alpha, beta, gamma, and delta. So those exponents are, those are given by a specific CFT. So there's a CFT that describes this critical point. There's a different CFT for 2, 3, and 4 dimensions. And we can calculate all of these from delta sigma, which is the correlation between two spins as a function of distance, and delta epsilon, which is another parameter in the CFT. Both of these are called scaling dimensions. You can use them to calculate your critical exponents. So in 2D, we know these exactly, and we can find all of the critical exponents exactly because the 2D Ising model has a lot of nice properties. Lars Onsager, who was a professor here and I believe is buried in the cemetery a few blocks from here, was the first one to do this. In D equals 4, it turns out that an approximation you can make called mean field theory tells you everything you need to know about your system. It ends up being a perfect approximation. But in 3D, this is tricky. 3D, we have some probably irrational constants, but the 3D Ising model is very important, as is, water. I hope I don't need to convince you why physicists care about water. Here are some constant values that tell us everything we could possibly hope to measure at the critical point. These were first computed by David and some collaborators about 10 years ago. And we've recently been able to refine the precision. So now we know these to much higher numerical precision. So that's that for critical points. We'll come back to it. And now I would like to introduce conformal transformations. So here's a question I'd like you to ponder for a second. why does Google Maps use the Mercator projection? I promise this is going somewhere. So think about it. Like the Mercator projection, which was invented by 17th century Flemish cartographer Gerardus Mercator. Imka's probably going to be very mad at me for mispronouncing that. It's great for navigation. Except it's like garbage for everything else. It massively distorts the scales of different continents. Here, Greenland appears roughly the size of Africa, when in reality it is 14 times smaller. Antarctica is massive. The engineers at Google are probably pretty smart, so why did they choose this one? Like, here are several great equal area projections they could have chosen, and also Gull-Peters, which is also equal area, but quite bad. The answer becomes clear when we look at individual neighborhoods of these projections, and we see that there's a lot of shearing going on. So near the poles, things are horizontally squashed, while near the equator, things are vertically squashed. And if you zoom in on your neighborhood, two streets that meet at a right angle in real life are not going to meet at a right angle on the map. But for the Mercator projection, they do. That is because the Mercator projection is something called a conformal map of the sphere. On a Mercator projection, two streets that meet at a right angle in real life will meet at a right angle on the map. At every point, space is zoomed in or out. It's scaled, but it's not sheared. There are, in fact, a lot of transformations with this property. This is a general property of, for instance, holomorphic functions on the complex plane. And there are a lot of other map projections with this property that the engineers at Google could have chosen, such as the Pierce-Quinn-Sunsenal projection. I have no idea why they didn't. It's so much nicer. Come on. So for the physicists among you, the conformal transformations of Euclidean space form a group generated by translations, rotations, dilatations, or rescalings, and what are called special conformal transformations, which are translations conjugated by inversion about the unit sphere. So in general dimension, we have these commutation relations. This algebra is isomorphic to SOD plus 1, 1. So the 2D global conformal group is isomorphic to the Lorentz group. Although in 2 dimensions, things are kind of complicated because the conformal algebra admits a symmetry enhancement to the Virasoro algebra, which is infinite dimensional. But my talk is about 3D CFTs, so I'm not going to get into that here. So now, last step of the preliminaries, I'm going to introduce quantum field theories and conformal field theories. So what's a quantum field theory? A quantum field theory is what you get when you try to combine relativity and quantum mechanics. Now, on its face, this doesn't seem like it should be so hard, but at the energies where we have to take relativity into account, we also have to take pair production into account quantum mechanically. So you go from theories describing the interactions of individual particles to theories that have to account for particle production and annihilation. As for an example of a QFT, well, I'm technically a particle physicist, so I am contractually obligated to show you a picture of the standard model in all of my talks. This is a QFT. This is our best understanding of all physics except gravity. And we have a bunch of individual particles that you can create from it. We have matter particles, force carrier particles. We have the Higgs, which gives everything else here except the photon and gluon mass. Or we don't know about the neutrino sector. We're getting to it. And yeah, this is a QFT. It is made of several smaller QFTs like QCD and electroweak theory glued together. But in general, like a QFT is the sort of thing that the standard model is. If we want to formalize this a bit more, we can get to QFT by quantizing classical field theory. We can get to it by taking quantum mechanics and giving it Lorentz symmetry. And alternatively, we can start with a statistical system like the Ising model that I showed you earlier, or like water near its critical point, and try to do statistical mechanics on it. And yeah, we get something that is mathematically equivalent to a QFT. And what all of these theories have in common is that their observables are correlation functions sometimes called Whiteman functions, depending on whether you subtract out the connected terms of space-time. So in the Ising model, everything we can observe can be, in principle, calculated from the correlation of two spins as a function of their separation. So let's go into each of these pictures in a little more detail. I do have a lot of results to get to, so I am going to go through this somewhat quickly. If we take a classical field in theory and quantize it, well, it's just the same as doing quantum mechanics, except instead of a Lagrangian, we have a Lagrangian density. Instead of ODEs describing the motion of particles, we have PDEs describing the motion of continua. Our observables are still Hermitian, except now they are Hermitian-valued functions of spacetime. We are still taking their expectation values, except now those have coordinate dependence, so they are correlation functions. We are still computing transition probabilities, except now we have, again, space dependence to take into account. So we're really computing scattering cross sections. And like in normal quantum mechanics, we can still do perturbation theory. We end up, like, if we want to calculate something in a QFT, that's a sum over Feynman diagrams that you can determine from a path integral, which some of you may have seen before. And what you're seeing here are basically like really like graphically dressed up ways to compute multi-point correlation functions of operators. And in general, in this framework, we have to do something called renormalization, where we relate the behavior of theories at different scales. We are the standard model, for instance, is an effective field theory. We know it does not describe nature at all scales. So we can make an RG flow diagram describing the differences at different scales. How physics changes as we change the scale of our experiment. This is not for the standard model. This is for the n=1 Gross-Naveau-Yukawa model, which I will get to near the end of this talk. And in one of these diagrams, if we renormalize a QFT, that RG flow space might have fixed points. And a fixed point is, if you ask yourself, what does a fixed point mean in this context? Well, a fixed point is just a scale invariant theory, and that ends up being a CFT, which I will get to in a few slides. So in the second sort of path to getting quantum field theory, we take quantum mechanics, then we endow it with Lorentz symmetry. We do a bunch of group theory. Our states fit into representations of the Poincare group, the inhomogeneous Lorentz group, because well, our theory has Lorentz symmetry. And this can't tell you everything because you can only do it exactly for like for a free field theory and a few other classes of field theories. But this can tell you quite a lot just from Lorentz invariance. There's a program now known as the amplitudes bootstrap, closely related to the conformal bootstrap, that is attempting to constrain all of QFT just using these like symmetry principles. And one thing I should note about internal symmetries, they cannot mix with your space-time one thing I should note about space-time symmetries is that they cannot mix with your internal symmetries. If your theory has some additional symmetry, maybe you're able to like rotate maybe you're able to apply some transformation to the electromagnetic vector potential. The generators of that have to commute with all the generators of your space-time symmetries. So really, like, we can't, like, space-time symmetries are special is what I'm saying. But there is an exception to that, and that is, the exception to that is conformal field theory. And in the third picture, I'm not going to go into all the math here because I only have so much time, but in the third picture, if we try to do continuum statistical mechanics, well, we can start with a model on a lattice. We can take the continuum limit. This is for the XY model. It's a close cousin of the Ising model, except our vectors are allowed to rotate rather than just flip up or down. And if we want to calculate the partition function, which gives us all thermal observables we could ever ask for, we we replace the energy term with an integral over the energy density. And what we see is that this object here looks eerily like the path integral from QFT that gives us Feynman diagrams. And in fact, it is the path integral from QFT up to an analytic continuation. If we just continue one of our coordinates to imaginary time, we can turn a classical system in d dimensions into a QFT in d-1 space dimensions and 1 time dimension. There's something called the Osterwalder-Schrader theorem that says for sufficiently well-defined theories, you are always able to do this. Sufficiently well-defined has a big asterisk, believe me. Alternatively, if we have a quantum statistical system given by a density matrix, we can continue that to a QFT in 1 more dimensions, except where the temperature is, or sorry, beta, which is 1 over the temperature, defines the periodicity of one of our dimensions. In the low temperature limit, beta diverges to infinity, so we get a duality between quantum statistical mechanics in, say, 3 dimensions and a 3+1 dimensional QFT that we all know and love. So what can we say about QFTs? We generally classify them by their symmetries. So there are what are called global symmetries, which are degeneracies in Hilbert space. That means there is those are actually physical symmetries. There are gauge symmetries, which are redundancies in our description, but also show up in the Hilbert space because there are what are called large gauge transformations that still give you Hilbert space symmetries and conserve charges. They also have space-time symmetries. We might want to speak about, oh, does a theory violate parity? Does it violate C symmetry? The weak force, does it violate the product of those? The weak force, in fact, does both, as was discovered in the 1950s and I believe 70s. We can also classify theories by their coupling constants, like how strong the individual forces are. I see someone raising their hand. Carlton?
I have a question on how I should think of a field theory versus a quantum field theory. Should I?
You should save that till the end of this section. The standard model, for instance, has 19 free parameters. Those tune the masses of the particles, the strengths of the interactions. And if we vary some of those, we might get phase transitions in our theory. So a gauge theory can have different phases. It can be conformal, it can be confining, it can be in the Coulomb phase where we electromagnetism is, whereas QCD, on the other hand, is confining, so you can't have a free object with a color charge in the IR. So as for what a CFT is, I mentioned that we can't really enhance the space-time symmetry group in any way. The exception to that is if we don't have any massive states in our theory, we can enhance it to the conformal group, and we get a theory with scale symmetry and also conformal symmetry. In general, any unitary scale invariant system is also conformally invariant. This has been mathematically proven in 2 dimensions and is conjectured to be true in higher dimensions. So this is what I have just shown you is a scale invariant quantum field theory. Why should we care? So the first reason we care about CFTs is because they are fixed points of renormalization group flows. If we take a theory, if we renormalize it, we vary the scale, the effective coupling constants change, then a theory with a mass scale lives on some trajectory in this space. And the fixed points are CFTs. So CFTs are, in fact, waypoints in the general landscape of quantum field theories. Second, we are generally interested in symmetry. I just went into this, but CFTs, due to something called the Haag-Lopuszanski-Sonius theorem, are one of the 2 ways that you can extend space-time symmetries. The other is supersymmetry, which we will not get to in this talk, but trust me, it's very cool. The third is criticality. As I mentioned earlier, you can turn a statistical system into a QFT. if you turn a statistical system at a critical point into a QFT, then you get a CFT because it's scale invariant. And because of critical universality, better understanding CFTs tells us everything we could ever ask about critical points. Every critical point lives in a universality class. That universality class is described by a specific CFT. So if we better understand CFTs, then we know a lot more about the sort of phase transitions you can build in a condensed matter system. Another reason a lot of particle physicists care about conformal field theories is because they are holographically dual to theories of quantum gravity. If you take a theory of quantum gravity, such as string theory, you chuck it in anti-de Sitter space, which is a negative curvature spacetime. It has a space-like conformal boundary. You can push your states to the boundary. You can show that they satisfy something called an operator product expansion, which is really what it is the part of a CFT that makes its structure so nice. And you can actually translate any question anything you can calculate in the bulk into a calculation on the conformal boundary and vice versa. So for instance, n equals 4 super Yang-Mills theory, which is a CFT, is it is dual to type 2b supergravity in the bulk. This has been verified to 5 loop order, which is, for those of you who don't know, a lot. And also, we care about CFTs because they are interesting mathematically. So in 2 dimensions, as I mentioned, the conformal group gets enhanced to the Virasoro algebra that has a nice analytic structure. So you can actually perfectly axiomize a 2D CFT. You get something called a vertex operator algebra. And you can use that to prove theorems in analytic number theory. So monstrous moonshine, which is a correspondence between the representations of large sporadic groups and modular forms, such as the J function here, was proven using something called the Frankel-Lapowski-Merman vertex operator algebra, which is really just a CFT. Of course, you can only do this in 2D, which sometimes makes it annoying when I talk to mathematicians. Like, I'm like, oh, I study CFTs. And they're like, oh, vertex operator algebras, at which point I have to explain that I study 3D CFTs, which are not VOAs. It's a thing. So before I move on, are there any quick questions about CFTs or criticality or whatever? Okay, let's move on then. So if I want to calculate things about a CFT, well, as I saw earlier, I can calculate critical exponents from the CFT's scaling dimensions. Those scaling dimensions are parameters. I can also calculate other things about a CFT. So for instance, if my CFT has a Lagrangian description, I can read off its coupling constants. In that framework, it tends to be strongly coupled. Also, not all CFTs have a Lagrangian description. There's something called the 6-dimensional 2, 0 theory, which you can prove does not have a Lagrangian description. But most of the ones that give interesting universality classes in condensed matter physics do. We are also interested in their symmetries. So for instance, if we have a magnet and we are trying to classify, we are trying to examine its universality class. The universality class corresponds to the symmetry group of the spin. So the Ising model has Z2 symmetry in this plot. If I let my spins rotate in a circle, I get the O2 model. If I let them rotate in a sphere, I get the O3 model, also known as the Heisenberg model, and so on and so forth. And those all have slightly different scaling dimensions and give different critical exponents. This plot was, this is a plot from a paper entitled the ON Archipelago. For context, the bootstrap community tends to use nautical metaphors. We have islands, archipelagos, navigator functions, continents. More on that later. But what you can do is you can calculate the critical exponents just from knowing these scaling dimensions. And those generally depend on the symmetry of the theories. We are also interested in the spectrum of operators. In CFTs, there is something called the state operator correspondence. So the spectrum of states is the same as the spectrum of operators. Like in a general QFT, you can get a state by acting an operator on the vacuum. In a CFT, that map is bijective, which gives it a lot of additional structure. We can also look at universal properties of CFTs. So every local theory has a stress tensor that is conserved by Noether's theorem. We might also have conserved currents for other symmetries. We can also look at the OPE coefficients. I'll get to what that is next slide. And we might also be interested in dualities between CFTs, where like we find two CFTs that appear to be describing disparate phenomena, but we can translate the calculations in one into calculations in the other, and vice versa. So I'm going to go into a little more mathematical detail here. So just a reminder, the observables we're interested in are correlation functions between operators as a function of where they are in space-time. So in general, every operator has a spin, which describes how it rotates, and a scaling dimension, which describes how it transforms when you zoom in or zoom out. So for instance, like constant numbers have scaling dimensions of 0. Stress tensors have scaling dimensions equal to the space-time dimension because in general, if you're looking at the energy density, you expect that to be proportional to the cube of your length scale in 3 dimensions. And primary operators, which is operators that are not derivatives of other operators, we can generally organize our operators this way. They admit what's called an operator product expansion, where I can take 2 operators that are inserted at different points. So I have O1 here of x, O2 here, which is inserted at point y, and assuming some fairly easy to satisfy convergence criteria, I can translate this into a sum over operators inserted at, well, whatever point I choose in the neighborhood of x and y. And what that means is for a correlation function like this, I can repeatedly apply the operator product expansion. I can turn 5-point functions into a sum of 4-point functions. I can turn 4-point functions into a sum of 3-point functions. I can turn 3-point functions into a sum of 2-point functions. And I can, in principle, calculate any observable, literally any observable, just by repeatedly applying this OPE. So in general, the scaling dimensions, and it's fine, just keep going. No. Okay. In general, all of the observables of your CFT are specified by just the set of operators, spins, and OPE coefficients. There's an infinite set, but if you know it to perfect precision, you can calculate literally everything about your CFT in principle. So if we look at some specific correlation functions, we see that 2-point functions have to have this form. We can always pick a basis of our operators such that the 2-point function of 2 operators is a delta function over the separation to the 2 delta when the operators are the same and vanishes when the operators are distinct. 3-point functions are also kinematically fixed, except there's an additional degree of freedom, which is the OPE coefficient between O1, O2, and O3. These H's are just given by the scaling dimensions of the operators. For spinning operators, it's a little more complicated. I might have additional structures, and in general, for spinning operators, I have multiple OPE coefficients for each non-vanishing 3-point tensor structure, but it's schematically the same. And for 4-point functions have an extra degree of freedom, so we need to be a little more careful. So 4-point functions, what we can do is we can, in any number of dimensions, there is enough freedom in the conformal group to put all of our operators in the same plane, fix the positions of 3 of them, and but like no more. So we can always fix 3 operators, but the 4th is just somewhere else in the plane. So our 4-point functions are functions of this parameter z. Here, z is a complex number. The horizontal part is the real component. The vertical part is the imaginary component. And we get the 4-point function is still fixed by our conformal data, but it's a sum over these special functions called conformal blocks. Here, what we can do is we can OPE O1 and O2, as well as O3 and O4. And yeah, we get a sum over conformal blocks. In even dimensions, these conformal blocks are hypergeometric functions. In odd dimensions, we don't know them exactly, but we have convenient series expansions. So getting a little less technical, I'd like to introduce something called the bootstrap. So in general, in physics, we build a model, test it against observations, and we iterate. But there's also another way. We can say, given that our model agrees with itself and satisfies some like basic assumptions like conformal symmetry, unitarity, yada, 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 we can say, given that our theory agrees with itself, what can we then say about it? So this is actually a fairly old approach. It originated with a 16th century Flemish mathematician named Simon Steven, who used it to calculate the force of an object on an inclined plane. What you can either solve it in terms of like Newtonian mechanics with like a free body diagram and everything else. That's really annoying because you have to add vectors. Or you can say, all right, suppose we have, so we know it depends on the angle. If we set up something like this where we have an inclined plane with 2 different angles of incline, and we put a loop of chains around it, then the force on the weights on this side times the density of these weights has to be equal and opposite the force on the weights on this side times their density. Otherwise, there would be a net force one way on the chain, and it would loop around, and we could get energy from nothing. In reality, we do not see this happening. Take my word for it. But this is a really creative way to derive this law. We know that it has to be sine of theta, because otherwise our theory makes no sense. And so we can now apply this to theories in high energy physics. So we can ask, if we have, say, a theory, suppose it's a CFT, and we say all we demand is that it agrees with itself, what can we say about it? And for CFTs, we can say quite a lot. So recall that we have an operator product expansion. If we have a 4-point correlator, O1, O2, O3, O4, where all of these are inserted at different points in spacetime, we can OPE it in 2 different ways. We can begin by OPEing O1 and O2, or we can begin by OPEing O2 and O3. So we're applying a decomposition that we know is convergent and we know should work. But what we end up getting is we get 2 different infinite sums over our conformal data, which we know physically they have to be equivalent, but they're not manifestly equivalent. One could imagine that if you write down a random set of conformal data, this wouldn't be satisfied. And indeed, that's what you actually see. It turns out that it's actually quite hard to satisfy these constraints. And if you just write down a random conformal field theory, just the set of conformal data, it's not going to agree with itself. And we can use this. I'm not going to belabor the mathematical details too much, but in general, for this toy model where all of our operators are identical, we eventually get a sum over lambda squared times some linear combination of the conformal blocks. We know that this has to sum to 0 at all points z. We know that lambda are real because that's implied by unitarity. And what we can do is if we can find some linear functional acting on this that is strictly non-negative and positive at least one point where these OPE coefficients don't vanish, then what we've shown is, well, we have a sum of something positive times something else non-negative. That can't possibly be 0. It has to be positive because we're just adding up positive things. And it turns out that you can actually pose this as a linear programming problem. You take a CFT, you convert it you say, given that this is self-consistency, what can we say about it? You make some assumptions about your theory. You get a linear programming problem, which is, for those of you who don't know, just a system of like trying to satisfy a bunch of linear inequality constraints. We have nice, very efficient interior point methods for them. And yeah, what we can do is we can make some assumptions about our CFT, convert it to a linear program. If it has a feasible point, then we haven't ruled out our CFT. If it doesn't have a feasible point, we have. And we can use that to say non-trivial things about our theory. So this is known as the conformal bootstrap. In general, if I have like different operators in my correlator, like this was for sigma, 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 but if I have like sigma, sigma, epsilon, epsilon, or whatever, I get something called a semi-definite program, which is a generalization of linear programming, but still has like a lot of nice, efficient interior point methods. So in general, the way we actually bootstrap a theory is we pick a theory and pick some correlators in it. We say we impose crossing symmetry. That's the self-consistency constraint I mentioned earlier. We impose any other symmetries the theory might have, say a Z2 symmetry for the Ising model or an O3 symmetry for the Heisenberg model. We impose some assumptions on the spectrum of our theory. Then we convert it to a linear program or semi-definite program, see if there's a feasible point. If this is generally a truncation of the system, so it might give false positives, but it never gives false negatives. And then we can repeat with different spectrum assumptions to actually like figure out the spectrum of our theory. So in the Ising model, for example, we can pick values of delta sigma and delta epsilon. We ask our linear programming solver, is there a point, is this point allowed? And it gives us back either yes or no. We eventually get a little island of yeses, which we can shrink by increasing the numerical precision of our system. And it turns out that you can use that to calculate the critical Ising model. You can use that to calculate the critical exponents of the 3D Ising model. Remember those irrational looking constants I showed quite precisely. So we've learned something about the Ising model without needing to do any like experiments or perturbative calculations. Pretty cool. So what can we do with it? So now I'm going to talk about the work I did for my thesis. So first off, what we can do is we can look at global properties of CFTs and see how they constrain the Ising model. So every local theory has a stress tensor. So if we bootstrap correlators with stress tensors in them, we can place global bounds on CFTs. This is especially useful for bounding like the central charge, which is a measure of the degrees of freedom in a CFT. And this has been done about 8 years ago by David and some collaborators, where they just looked at correlators containing stress tensors and nothing else. And they got this like nice allowed continent in terms of the lowest parity even and parity odd scaling dimensions. So what we could ask about this theory, or what we could ask is, okay, how do we apply this to specific CFTs? Like the Ising CFT. Now, to access individual CFTs in this continent, you will need to also bootstrap scalars such as sigma and epsilon. So here's, if you want to bootstrap the, if you want to do the stress tensor bootstrap and the Ising bootstrap at the same time, here are all of the correlators you need. Each of these OPEs gets pretty complicated. The OPEs of spinning operators generally have several 3-point tensor structures. One sec, let me find where I am in my notes. And when we build 4-point functions and look at all of the combinations of those, we get a very, very large system. So this required a lot of engineering in our bootstrap code. We need, like, computing the conformal blocks at this precision becomes a non-trivial task. So we had to build a scheduler and build like dependency trees for different components of, build like dependency trees for different components of conformal blocks. And this required a significant re-engineering of our bootstrap code. but once it also required a lot of compute time. I don't think we kept track, but something on the order of 10 million CPU hours. Very grateful to Expanse at the San Diego Supercomputing Center for giving us that time. And when it's all done, well, the first thing we get is a new island. So we managed to shrink the highest precision Ising island by a factor of 100. So this little red island is what we now see. What this tells us is that introducing stress tensors gives you much more precise bounds on your critical exponents compared to just bootstrapping scalars. And also, we can access new sectors of it. So this continent I showed you earlier, it has, this is a plot of the parity even and parity odd spectral gaps in different CFTs. And what we might ask is, okay, where's the Ising model in this continent? Because we don't know what its parity odd sector looks like. Building parity odd operators in the Ising model is tricky. In the lattice framework, you would have to build like some weird configuration of spins that like is chiral, and then you would have to take the continuum limit properly. And it turns out these operators are quite hard to build. The scaling dimension of delta epsilon, the parity even operator, is at 1.51. So it's pretty easy to access in our CFT. But if we look at the lowest parity odd operator, well, in the corresponding free theory, it has a scaling dimension of 11. Perturbative estimates in the actual Ising model give something similar. So what we can ask is, well, where actually is it? And we can read it off from this stress tensor map. So this is a plot of this is a plot of delta odd and the gap assumption to the next parity odd operator, which is something we have to put in to get upper bounds. And what we see is that for all but the most conservative gap assumptions, we find that the parity even operator is located at 10.929. Or sorry, the lowest parity odd operator has scaling dimension 10.9293, which is pretty similar to the free theory. So the Ising model it has a lot more parity even operators than parity odd operators, low in its spectrum. And also we can say that we have a way of saying that it is like 1.38% fermionic. I can go into more detail about that during the question section. And if we want to locate it in this continent, well, if we're asking like, okay, in this continent, where is the Ising model? Where is it in our space of theories? We actually see that it's pretty, if we pick out 10.93, it's pretty close to the upper bound here. In fact, it's right here. I've zoomed in on the shoulder of this plot. So what we can say is that for its value of delta epsilon, the Ising model approximately maximizes delta odd. Now, this is at finite numerical precision, so maybe it doesn't exactly, so it's highly suggestive that it exactly maximizes delta odd for its value of delta even. We can also look at stress tensor OPE coefficients in this space. We see that the Ising model lives at this kink where we try to maximize lambda TT even as a function of the gaps. We see that there's another kink giving the free scalar and another kink over here, which might correspond to an interesting theory, but we don't know which one. So this is highly suggestive. I'm a little short on time here, so I'm going to wrap up the Ising section and jump into gross niveau Yukawa models. So if we zoom out a little bit, well, yes, our theory is invariant under that, but if we zoom out a little bit, we can say, okay, suppose we're trying to build a CFT. We are trying to build a system with a critical point, and we want it to contain fermions. Because everything I've showed you so far is made up of scalars, but electrons are fermions. And, well, condensed matter physicists care a lot about strongly correlated electrons. We can ask what order parameters they have, which is a very important thing you might want to know about a phase transition. And we can ask, okay, if you break the symmetry in one critical point, can it flow to a different critical point? So yeah, so what we're setting out to do here, what I did for my PhD, is I classified critical points satisfying certain assumptions that are built of fermions. So there's a very basic a basic building block, like one of the simplest CFTs you can write down with fermions and a critical point is called the Grosnovo-Yukawa model. This is this gives a universality class that shows up in a lot of condensed matter systems. So we see it in topological insulators. We see it in, there's a lot of new work on graphene and identifying G and Y universality classes in that. This has an ON global symmetry. I should walk you through this Lagrangian actually. So we have a kinetic term, mass term. Here, phi is our order parameter. It's a scalar. We assume that there's like some scalar that attains a vacuum expectation value as we cross a phase transition. And that is Yukawa coupled to a set of fermions with global symmetries. These little i's here are an ON index. These here are Majorana fermions for reasons I'll get into shortly. It turns out if you write down this model using Dirac fermions, it factorizes into a Majorana fermion model. And again, this is a universality class that shows up all over the place. So here is here's a transition between here's a quantum critical point describing the boundary between two different superconducting states in D-wave superconductors. Here the coupling goes as x squared minus y squared. Here is a different, a qualitatively different superconducting state. Oh, this is from a paper by, I believe, Herbert in 2006. I forgot to include the citation. Previously, there has been some bootstrap work on Grosnovo-Yukawa models. So we identify several operators. We identify our fermion, which is an ON vector. We identify sigma, which is a parity odd scalar, and we identify epsilon, which is a parity even scalar, both of which are singlets under the ON symmetry. Yeah, we equate these with phi and phi squared in the Lagrangian description. Often at critical points, there's some mixing, so we can't make that equivalence exactly, but it is a useful first order approximation. We have the following non-vanishing correlation functions as well as all of their permutations. And previously, David, as well as Rajiv Aramili, who was a former grad student here, who some of you might know, and several collaborators, bootstrapped these models for n equals 1, 2, 4, and 8. They obtained islands. Here is the islands in delta psi, the fermion scaling dimension, and delta sigma. We see that these agree reasonably well with the epsilon expansion, but less well with the large N expansion. These are 3D islands because, like I said, we had 3 scaling dimensions. So these islands also extend into delta epsilon space. Here is a different cross section of the plot. And yeah, we have very precise estimates of their critical exponents contingent on some assumptions about the spectrum of the theory. So one question we might ask is this like a normal critical point, or is it a tricritical point? Could we, by potentially extending the phase diagram, have an additional parameter that we might need to tune to reach it? What is the geometry of phase diagrams containing G and Y critical points? What that generally corresponds to is another relevant operator, meaning an operator with scaling dimension lower than the space-time dimension in the spectrum of the theory. And at n equals 1, that is the case. The second parity odd scalar is relevant. At n equals 1, this is also the super Ising model, so we have emergent supersymmetry. At n equals 2, we actually don't know. So here are some Pade approximations for the parity odd spectrum of Grosnovo-Yukawa models as a function of n. These are combining the large n behavior as well as the exact n equals 1 results, which are easier to calculate because of the emergent supersymmetry. And At n equals 2, we're not sure because these perturbative estimates give a value very close to 3. But it turns out the answer is no. So this is a little hard to see up here, but what I did, I computed lower bounds on the next parity odd scalar, and we see that all of them are above 3, which means that this model has exactly 2 relevant scalars. Or it has 2 relevant parity odd scalars, and if we repeat the same analysis for delta epsilon, we see that it does not have another relevant parity even scalar. And this is true at all n greater than 1. So for all n greater than 1, every GNY universality class in the phase diagram has to have codimension 2. If you are tuning 3 parameters to reach it, it is a line. If you are tuning 4 parameters to reach it, it is a plane. If you are tuning 2 parameters to reach it, it is a point, which is useful if you're actually trying to build these things. But that's just for GNY universality classes. It is also possible to extend this model. So one thing you could do is you could say, OK, phi is now a vector, like in the Heisenberg model or the XY model. We could also say that when phi gets a vev, it maybe breaks the, what if it's like a parity, what if it's a space-time parity even singlet, but it getting a vev breaks the flavor symmetry to some smaller group. So one example of that is it turns out that if you write down the model with Dirac fermions, then in 3D, it actually factorizes to this thing, which is just what I described. This has ON/2 squared semidirect Z2 symmetry instead of ON. This is called the chiral Ising model, or chiral GNY, and it's perturbatively very similar to the GNY model, but it has different symmetry behavior. So can we do more? Why this clicker is being weird. Okay, that part's still working. There we go. Okay, so what we're going to do is we're going to assume that phi is a flavor vector with m components. It transforms in the vector representation of some global symmetry. We start with a coupling with Dirac fermions, and we look at the possible symmetry enhancements that we can get. And if we take m equal to 1, okay, I think this clicker is, one of the buttons is stuck on the clicker. I think it's fixed now. Okay, if we take m equal to 1, yeah, I'm going to use my laptop. Okay, there we go. Yeah, if we take m equal to 1, then we can, depending on how we write the coupling, we can get 2 different models. One is the GNY model, one is the chiral Ising model. This corresponds to 2 different things you can build depending on the specific shape of the Yukawa coupling. And what I did in my PhD, I completed a group theoretic classification of this, of all of the couplings you can get by starting with Dirac fermions. And I obtained 12 different Lagrangians you can write down up to symmetry enhancements. 6 of these have fixed points in the 4 minus epsilon expansion. And of these, 4 are well known in the literature and 2 are new. So the first is the GNY model itself. This has ON symmetry. Here, n is 4 times the number of Dirac fermions because there's a Majorana factorization when you restrict yourself to 3D. You can also obtain the chiral Ising model, as I showed on the last slide. It is also possible to obtain this quarter GNY model where I take the 4 Dirac fermions, or the 4 Majorana fermions that this Dirac representation factorizes into. I switch the sign on one of them, and I get something with O3n semi-direct, or sorry, I get something with O3/4 n cross O n over 4 symmetry. And these all have identical perturbative data at low loop order, but at very high loop order, they have different conformal data, and in addition, they have they also have okay, they have different symmetry groups. Mouse is okay. Trackpad is working. In addition, if I allow phi to have multiple components, I have multiple scalar fields. I can get the chiral XY model. This is well known in the literature. You can find it in graphene. You can also have the chiral Heisenberg model, and we get a new model, the 3-1 Heisenberg model, where I have where I treat one of my Majorana spinors differently than the other 3. So I then have phi here has 3 components. I have a Yukawa coupling of chi phi psi 1 plus chi phi psi 2 plus chi phi psi 3. And this actually has, here we go, very similar. It has qualitatively similar but quantitatively different behavior to the Heisenberg model. So here's the Heisenberg model on the left in G and lambda space. It has a fixed point up here. Here is the 3-1 Heisenberg model on the right, the new one I discovered. It has a fixed point here. It also has, let's see, this one has it has UN cross O3 symmetry. This one has ON cross O3 symmetry, despite the fact that you can build both from like, I guess, pretty similar couplings with Dirac spinors. And in the future, I am working on the code now. We hope to bootstrap these and build just a big atlas of critical points with fermions and scalar order parameters. Oh, right, this isn't working. So what's next? A little short on time here, so I will wrap up very quickly. First off, in the stress tensor bootstrap, there are a lot of things we can do. We're currently working on extracting the extremal spectrum, as well as looking at substructure in the CFT continent. Remember the plot I showed you where we're trying to maximize lambda TT epsilon. So David and I, given how much new bootstrap technology has been developed for this, are currently working on a setup for current and parity violating CFTs with Naveen Umasankar, who I believe is in this room. Hi, Naveen. We may also try external parity odd operators. And also, what we've bootstrapped is a correlator of stress tensors. That is the same thing as an energy correlator, which is very important in the particle phenomenology community right now. And in GNY, the new models I showed need to be bootstrapped, as do the chiral Ising, chiral XY, and chiral Heisenberg models, where we have fairly good perturbative expansions, but no non-perturbative bootstrap computations. Now that we've completed this classification and we've improved our bootstrap technology for the stress tensor bootstrap, this should be much easier. I'd also like to talk about what we can do now with our bootstrap technology. So we can apply it to the phase diagrams of gauge theories. So some of you might know QED in 3 dimensions displays qualitatively similar behavior to QCD in 4 dimensions. You get confinement, above which you get a conformal window in the flavor number. So this transition is thought to be mediated by chiral symmetry breaking. But for QED3, which is a very useful toy model of confinement, we don't know what the critical flavor number is. And this is hard to study perturbatively because it's strongly coupled, and it's hard to study in lattice computations because of fermion doubling, which presents an opportunity for the bootstrap. So here are a bunch of different estimates. We see them ranging from 1.5 to 6.6 using different methods. There's an upper bound of 10 from the functional renormalization group, as well as a perturbative estimate of 4. And I think the ones I most trust here are between 2 and 4. So some initial work on this has been done by David and some other collaborators, Rajiv, Soner, Yuan, and Shijin, all of whom were either grad students or postdocs in this department. Accessing the gauge information is hard because gauge symmetries are not symmetries of the Hilbert space, so you have to use monopoles, which are charged under the large gauge group, and you get an island for some very aggressive spectrum assumptions. You also get some disagreement with the Monte Carlo results, but again, Monte Carlo with fermions is hard. And if you look at the space of the scaling dimensions of the 2 lowest charge monopole operators, you get a peninsula, and it's hard to isolate your theory, we think, because there's this non-local deformation, which looks superficially similar. And now that we have improved bootstrap technology, we can, now that we can deal with spinning operators very nicely, we can attack this directly. So that's what I'm working on now. There are a lot of interesting places we can go with this, and I really like that the bootstrap allows you to basically do experiments on theories. It's a fun way of doing physics. Crap. Okay, I got some. Where's my mouse? Okay, I lost my. There's my mouse. So, just like to wrap up a little. First off, I'd like to acknowledge some of the people without which I would not be here. So I didn't do a photo slide, but I have something I'd like to read. So first off, I would like to thank David Polin for being just the best advisor I could ask for. I really have learned so much here, and I really appreciate David for always giving me room to grow and just really teaching me how to think about QFT. I would also like to thank the rest of my thesis committee for taking the time out of their very busy schedules to see this project to fruition. Your advice has been excellent, and I have learned so much. I would also like to thank my many colleagues at Yale and elsewhere, particularly Rajiv Aramili, Yuan Shin, and Jijin Lee, who I believe are watching over Zoom, as well as David Simmons-Duffin, Aika Liu, as well as a lot of the people in this room. I'm not going to read all of your names out, but you know who you are. You're all wonderful, and I love you. I love you guys so much. I would also like to thank the many friends I have made in my time at Yale. So that means the people in my cohort. I know it was weird coming in during the pandemic, but I'm really glad we made it work, and I could not have asked for a better group of people to go through grad school with. I would also like to thank Mark for putting up with me as his office mate all this time, and for always being an incredible sounding board. Yeah, I really have to thank all of the professors that I've either taught for or and all of these students who I have really enjoyed working with and who have just taught me so much. I really learned to love teaching while I was here. I also have to give a shout out to Rose Powers for being a big part of the reason why that happened. And yeah, I also must thank my union, Local 33. I am so proud of what we've built together. I believe 33 organizers account for roughly half this room. Thank you so much. I am so blessed to be here. I also have to thank my many teachers from high school and elementary school, particularly Julie Eckhoff, for really teaching me how to actually write a paper. And Scott Parker, my undergrad PI, for teaching me how to get a paper into a journal. Again, I'm getting kind of emotional right now, and I know I'm over time, but I love you guys so much. And lastly, I absolutely have to thank my family, especially my parents, Cecilia Cadet and Stephen Mitchell. You guys are the best. I love you so much. I really couldn't have like asked for better parents. All right, and with that, thank you.
Great. Thank you, Matt. Are there any questions from the audience?
Yeah, thank you for a very nice talk, Matt. Yeah, I was curious if you mentioned a bit about lattices in 2, 3, 4 dimensions, and you spent so much time talking about CFTs in higher numbers of dimensions. I was wondering if you could comment at all about lattices and even larger number of dimensions, say something random like 24-dimensional Euclidean space.
Thank you for that question, Mark.
You're welcome.
So, some of you might know I'm a huge fan of the Leech lattice, and I mentioned earlier that 2D CFTs were instrumental in the proof of monstrous moonshine. What you can do is you can take a 2D CFT, compactify it on the Leech lattice, which is a special object that I'll define in a minute, and it has monster group symmetry. In addition, if you try to pack spheres in any number of dimensions, well, in 1D, like spheres are just line segments. In 2D, it's hexagonal packing. In 3D, it's hexagonal close packing. 4D, we don't know. 5D, we don't know. 8D, it's the E8 lattice. And in 24 dimensions, there is a remarkably efficient packing called the Leech lattice. It is, there are many ways to construct it. It is, I believe, the unique 24-dimensional unimodular lattice that does not contain a root system. And yeah, it gives the most efficient packing. And the proof that it's the most efficient packing can be translated into a conformal bootstrap problem, because the functionals that Mariana Wiazowska used to prove that are really just dressed up 2D conformal bootstrap functionals. I love the Leech lattice. Oh, do I? Let's see, someone's in the, oh, Matt. Yeah, Matt, can you unmute yourself?
Yes. Hey, Matt. Great talk. And looks a lot of great work that you've done. It's been a pleasure knowing you for a few years now. A question on kind of the conformal bootstrap method generally. So since it's like based on those self-consistency constraints, can you end up in a situation where a constraint doesn't give like a single allowed value of the CFT data, even if you were to suppose that you had like infinite numerical precision? So I'm wondering,
Yeah,
like,
so
are those
what you
islands like a mathematical or computational limitation?
Yeah, so that's actually like a really good question. You can get one parameter families of CFTs in a lot of different ways. So if you allow yourself to violate unitarity slightly, then you can actually like, let's see, you can deform the ON model continuously. There are what are called TT bar deformations in 2D, where you add like a TT bar term to your Lagrangian. Let's see. Wait, I should. Oh, if you relax locality, then you can get a one parameter family of what are called generalized free field theories. So yeah, if you allow yourself to just like not have a stress tensor in your spectrum, and then like you can get like, yeah, then the free scalar theory itself is no longer fixed by self-consistency. So yeah, that generally speaking, that is a way to like, that is a thing you can do. I'm rambling. Thank you, Matt.
Yeah, thanks, Matt.
Can I ask a question?
Who was that?
Xuan.
Hey, how's it going?
Hey, good. Yeah, very good talk. Yeah. Yeah, so my question is, yeah, so it's kind of like an open thing. So yeah, I just wonder. So like you tried like bootstrapping like operators like with spin, stress tensor, like yeah, all of that. So basically like building up precision on a theory that is like already surrounded, like getting an island. If you want to let it like shrink, what do you think will be the best? Like increase lambda or increase like the number of operators in the mix or doing something like more creative? Just curious. Yeah.
Yeah, so there are several things we could try. I have most of the code for this. We could try putting AA bar in the spectrum and running it at higher lambda, which is a lot faster now. This is very speculative, but we could try we could just try the mixed scalar stress tensor correlators, except now where the scalars are charged under the topological and global symmetries. That's really just it's the space-time structures from the stress tensor code and the flavor structures from the QED3 code. And I think it would be computationally intensive, but I think that because like the thing that is locking us out is probably this line of non-local theories. Yeah, I think that would presumably give us much better sensitivity to locality, which could cut our big peninsula down to an island. But again, we don't know until we try, as I know you know very well.
Yeah. So yeah, I'm just curious, like in general, like, okay, so just in terms of like numerical bootstrap will be like a kind of like a next step kind of thing. Yeah.
Yeah.
Yeah. But yeah.
Next steps, I mean, what I just said.
I mean, you have already answered, right? So basically, just like whenever I hear of you talk, I'm just like curious, like what they think. Like, so given what we have, like what would be like the next thing to try in the like numerics, like sharpening the precision, right? So people say like people running like Monte Carlo, for example, would say, yeah, so like you can keep increasing the computational complexity and things will scale like a power law. So here it's like, yeah, in Bootstrap, like I'm just like curious like how things are like built up like in the future. Yeah.
Yeah. Again, there is still a lot we could do to scale up the numerical complexity, especially because we are currently I/O limited in the computation of the conformal blocks. So I think getting around that potentially by writing the blocks to a RAM disk on each node is very promising. But we should talk more about this soon.
Sure. Yeah. Thank you very much. Yeah.
All right. If there are any more questions, one last question. Yep.
Maybe a naive question, but what sets the limits on how small you can make these islands? Is it purely a matter of
your compute time and whether the cluster admins will yell at you for overloading the file system?
All right. Why don't we thank Matt again for great talk. Okay, so this concludes the first part of the dissertation defense. Members of the public, if you want to hang out, can hang out in the first floor lounge. Otherwise, for the committee, we'll take a short break and come back in 5 minutes.
All right. Thanks for coming, everyone.